Hello everyone. I just want to make a video here about some of these problems from Chapter 2. Hopefully this little demonstration will give you guys some insights into how to do these set theory problems. Really, set theory, to me at least, it's so fascinating, and there's a lot of it that we don't end up talking about. We really just see some of the rudimentary stuff. But these kind of problems, I think that with a little bit of practice, it might become easy to you. That's at least the goal, of course. But I know that at the beginning, these problems can be quite challenging. And so hopefully this will elucidate some of the problems here. But anyways, we're going to use, as is our custom, we're going to use a Venn diagram in order to represent these sets. Here we're not giving any attention to how many elements might be in these sets. They're just kind of these sets that are floating around in outer space over here. In particular, that outer space that we're going to call is the universal set. And so maybe, for example, the universal set could be like all the real numbers, and so there's infinitely many of them. And then sets A, B, and C, they can represent some subsets of real numbers. Like maybe A is some kind of like positive numbers, B could be like even numbers or something. Oh no, I'm already screwing it up because then they wouldn't be drawn like this in the same shape. Maybe if you think about it, you can figure out why. But here we are dealing with sets A, B, and C. And in order to be hopefully a little bit more helpful, what I'm going to do is color code these. Of course, it's only going to be more helpful for you if you are able to discern colors. If you are not able to, then let me know. Maybe I'll try to do it a different way, or I'll use some colors that you can distinguish. And so here we have set C. The green one over here is set A. And then this blue one is set B. And then this kind of also U ended up being a green one. No big deal. But what we're doing now, we're trying to represent a given kind of a set. This set that we have, it's C union the set that goes B union A. And then this whole thing is now complement, like this one. And so if we could just think about some of the order of operations, here we should always prefer the parentheses over anything else. And then beyond parentheses, the order of operations, I feel like actually, to be honest, we will always use parentheses in order to distinguish these different orders that we should be doing. So here the idea is to focus on this set, B union A. Can you tell which set that would be? B union A? Of course, it should be everything that's inside of the green or the blue circles, and so it will end up being this kind of like an infinity shape. It's all of this stuff. And I'm going to end up coloring this in now, but then later I'm going to have to come back and maybe do something else with the colors, because we're going to take the complement at the end of all this. And so here what I'm doing is I'm shading in with the kind of gold color B union A. It should be all of this stuff. Now what we want to do is we want to take that one and we go union with C. And so now we need to also fill in everything that's inside of the red circle. Notice we've already gotten some of that because A union B already had some things in common with C. And so now we have colored in this thing. By now with all the gold, we have colored in everything here. C union with B union A. And now we want to take the complement of this thing. And so the complement of that, it means everything that's inside of the universal set that's outside of this configuration that we have here, C union B union A, which is all of this kind of a, what is this? It's almost like a ringish, like a there must be a name for this shape. It's like a Gordian knot or something. It kind of looks like a knot, like a strange knot. But anyways, everything that's outside of this shape that's inside of the universal set, notice it will be all of this black stuff, just the whole region that's outside of here. So in other words, what it will be is everything that's not inside of either A, B, or C. It cannot be contained in any of those. There would actually be another way of writing it just for fun. Why don't we write the alternative description for this same set? It would be A complement, because that's everything outside of A complement, intersected with B complement, intersected with C complement. And this was the thing, we had a name for this theorem, if you can remember it. there was a name for this theorem that allows us to, almost as it were, to distribute this complement inside of here. But whenever you distribute the complement, it ends up changing the unions into intersections like this. A complement intersect B complement intersect C complement actually ends up giving us the same set. So try to use your imagination for that one. But anyway, I want to carry on. Let's see another problem. And here we're just doing these without announcement. I'm just going to keep carrying on through these problems. Maybe I'll put some timestamps on this one later so that you can flip through. But anyways, we've got another kind of an example going on here. We're trying to determine what is the set that would be described as A intersect C with this kind of a situation. Here I'm going to do my best ability to illustrate these sets that we have, because we have this set U, and we're going to have to put some thought into this one, because notice we have letters as elements over here, lowercase English letters, or Roman letters, however you like to refer to these. We have, looks like for the universal set, I don't think we skip any letters up until K. A, B, C, D, E, F, G, H, I, J, K. It's all of those. And then we're going to have some of them inside of A, some of them inside of B, and then some of them inside of C. But you can see that inside of A, B, and C, we're missing some of the ones that are inside of U. So we could go ahead and figure out which ones are going to be inside of U that are not in these other ones. And then I'm also taking a moment to look through here and see if there's a place where all three of them intersect, A, B, and C. Do you notice a letter that's in all three of them? I just saw it right now, the letter that's in all three of them. So we should have kind of this triply overlapping region, which is here. And by the way that I drew these, that region ends up becoming quite small, and so I hope it's not too small, but I'm just going to redraw it here to try to get a bigger middle part so I don't have to write the letter too small that is there. And so we will go with something like this. There, it seems better because we don't have too many letters to deal with anyway. Do you notice that H is not in any of these sets? So it should be here just in the universal set. I will label these sets like U. Does it help you, by the way, to have the color coding? Because I have forsaken the color coding for this problem here. But whenever you draw yours, maybe you can use color coding if it helps you. And so for the universal set, we have, why don't I just color code some of the letters? Well, actually, then it's going to be hard to do the overlap. So here, the universal set, you notice it has H, because H is not in A, B, or C. It also should have K. See, none of those have K, so K is in there. Are there any other ones? A, B, C, D. What about E? I don't see E over there. E, F, G, H, I, J, K. So just by scanning these are the ones that are outside of A, B, and C, but they're still inside of the universal set. And then we have inside of A, do you notice that the letter A, it's actually shared. A is shared between A and C, so A should go in here, the lowercase a. It's shared between A and C, and this is the little area, this football shape over here, is the overlap between A and C, but then also this little triangular part in the middle overlaps B as well. And so we want to be careful about where we're putting these. Lowercase a, though, it's inside of A and C, but it's not inside of B, so it should be in this kind of a concave sort of triangle there. And then, what about C? The letter C is inside of A and B, I noticed that one, but it's not inside of C, oddly enough. And then what about the letter B? Do you notice that the lowercase b, it's inside of, over here, B and C, but it's not inside of anything else. And now going on to D, where is D over here? D is inside of A and B, so the lowercase d should be there, but it's not inside of C. So we don't want to put it in the very middle. And then we're on to E. E is actually outside of these, it's in the universal set. F is shared between all of them. Do you see it? F, A, B, and C, they all contain F, so it should be in this super duper middle there. And then we have G is where? I see a G inside of A. It's also inside of B A and B has G, but it's not inside of C, so we don't want to put it here where the F is. F has A, B, and C. And then that was G. H is inside of universal set, but not inside of A, B, or C. And then HI, we're on to I now, is inside of A and C. So the little I goes there. And then HI, J. Do you see it? J actually is kind of a lonely little guy. He's only inside of C. Which, by the way, do you notice that all of these letters, they're inside of the universal set, even though they're inside of these other ones as well? That's because A, B, and C, they are all subsets of the universal set. Do you notice it? A is a subset of the universal set. For example, we could say this one. And sometimes we can put these little caps on the U to distinguish this as a letter U instead of being the kind of a union-y shape. Okay, so just moving on. Here, all the time, we're planning on determining which set is A intersects C. And we could have done that without this picture, but I just like drawing the picture. It kind of helps us use our imagination a little bit. Have we done it? We got H, I, J, K. That's all the letters. And so now, we're wondering which set is A intersects C. A intersects C should be everywhere that is common between A and C. And so since A is here, and then C is this part over here, do you notice what they have in common? They share in common this kind of a little football-y shape right here in the middle. And which elements are inside of this little football-y shape? Of course, it is A, and I'm going to write it here now. A intersects C. This is the set that just has the A, the lowercase I, and the F, like this one. And so that would be our answer here. And now, we have another nice example. What an interesting picture this is. I like the color scheme as well. I like this kind of a, what color should this be called? Is it a lavender? Or it could be some type of fuchsia. I actually, now that I say fuchsia, I'm sure that I don't know exactly which color fuchsia is. But I think it might be that color. And so we have a universal set. We have an A, a B, and a C. Here they overlap quite differently than what we've had in the past couple of problems. We have some weird kind of shapes. They almost look like orbits of planets or something. You know, like how planets sometimes, A and B, they could be like orbiting orbits of a planet that's, or a sun that's in the middle or something, and this is a comet that shoots out and it goes way outside the solar system over here and then comes in. It was kind of reminding me of that. But anyways, we are using the numbers in the regions to indicate here the numbers of elements inside of there. So 2, 3, 5, 6, 11, and 12, those are not elements themselves. We're not using the numbers as the elements. That's how many elements are there. And so, you know, maybe there's like people or something. There's 6 people whose name starts with A or something like that. And so those 6 people are inside of this set. Here, why don't we think about some ways that we could relate these as far as talking about subsets. Of course, A is a subset of U. Always this will be the case. A, B, C, all of our sets should be subsets of the universal set. Or else that set is not very universal, is it? And then we have another relationship. Do you notice this one? And by the way, you can tell they're subsets right away because they are completely contained inside of U. And we have another containment. Do you see how B is completely contained inside of A? That means that B is also a subset of A. And then C, since C hangs out of both of them, we cannot say that C is a subset of either one. And then you notice that B also is hanging outside of C. It has 2 elements that are not inside of C, and so B is not a subset of C either. And so we would have these kinds of relations as far as subsets are concerned. Now what about this one? We have some numbers in these regions, and we are hoping to figure out how many elements are inside of A. Looking for that one, the number of elements inside of A. Well, do you notice that there are 6 elements inside of A that are not inside of B or C? But then these elements that are inside of B, there's 2 and 3 more of them, so there's actually 5 elements inside of B. I will say 2 plus 3, because these are inside of B, but B is also a subset of A, so they're in A as well. And then you notice 3 of these are inside of C, 3 of these elements that are inside of B, but then there's also 12 more elements inside of C that are also inside of A. That's why it's inside of this green circle. Everything inside the green circle is what we're interested in. So there are 12 more elements there that are in C also. And when I say inside of B, I also mean, of course, and A. And then as well with the inside of C, that means and A. Because here it's inside the intersection of A intersects C, those 12. And so if we add them all up, 6 plus 5 is 11, plus 12 more is 23. So that's the number of elements inside of A. And now we have one of these nice problems that we're calling survey problems from 2.4. How about this one? We're going to get kind of an easy one here. And then the next one coming up has a lot more details to be interested in. And so what do we have? There are 83 people protesting the destruction of the rainforests. Shall we join them? There are 34 males, 25 of whom are students, and then there are 21 female non-students. So we're interested in how many female students are protesting. We'll be able to figure it out from these numbers that they give us. Why don't we draw a little picture? I'm going to use the color scheme from the last one. I wonder if I have this fuchsia color. I think so, but I'll look for it later. We have, here do you notice the way that we are breaking up these demographics? There are males and females, and there are students and non-students. And so it's going to be kind of interesting to do it, but we should have, what about a blue color? It makes sense to do it. These can be the males, and then if I have a pink, oh, it's kind of pink. These can be the females. And yes, we're going to have males and females. I hope it's not controversial that I'm going with this sort of a breakdown. Males and females, and then we also have students. So students can be either males or females. And so I'm going to make this one become students. And so I'm going to call this set S, and then the males and females, of course, we can call like males and then also females. And then we have to put the same way that we had for the previous problem. Oh, this should be the universal set, by the way. For the previous problem, you know, we had these numbers that were representing the number of people that were inside of each of the sets. People or things or whatever, there was not context to go along with this previous problem. But here, we know that there are 83 people protesting in general. And we have that 34 are males, 25 of whom are students. So do you notice this one, males intersect with students? That's the people who are males and students. It says there's 25 of them. So the number of that thing is 25. There are 25 people who are males and students. Oh, I just noticed something funny about my picture. Now it's not controversial anymore, right? Because I made the males and females overlap. But then it will become controversial again because there's not going to be anyone in there. But anyways, there are 25 people who are males and students. So that should go here, 25. And then we know that there are 34 males total. So if we add up how many males are not students, which would be whatever's hanging out just in only the blue part, not also inside the black, there should be 34. So 34 minus 25, going through this thought process, there are 9 of them that are neither, or that are not students, that are males but are not students. And then we have 21 females who are not students. And so that's this group over here. And these are all the females who are not students. And then the females who are students should go into this little overlappy part right here. And so the number of females who are not students, it's going to come down to the fact that there are 83 people protesting, 83 protesters. we have already distinguished that 9 and 25 more and 21 more are not students or else are not female, because that was these groups: the males that are not students, the males who are students, and the females who are not students. So trying to figure out how many are left over. This all adds up to 55. And then 83 minus 55 is how much, everyone? Doesn't it seem like 28? And so that's actually the number. That's how many must be females who are students. There are 28. Because here some of these regions don't make sense. For example, how can you be a student over here but not be male or female? So it wouldn't make sense to have anything inside of that region. And really, the answer here, by the way, we figured out is 28. There's 28 people who are female students. Would have made more sense to draw this picture another way. Maybe we would give it a quick shot. The universal set, of course, there's nobody that's going to be just in the universal set and not in one of these groups. We should have the males, we should have the females, and I'm going to draw it where they almost overlap, but they don't. They're just adjacent to each other, and then the students would be like this one. Does it make sense? So here you have the people who are students, who are males, will be here. Students who are females will be here. Males who are not students, and then females who are not students will be on this little outer region there. And then we're not expecting to have anyone inside of this outer band here. And so that'll be a nice one. Now the last problem. I really want everyone to give this problem a shot. Kind of going through the process that we did for the previous one, but here we will have a little bit of a different picture because we've got these programs. For this problem, there's a fitness magazine. People are exercising, staying healthy during the Ronas. And the following results were obtained. So some of these young adults, there were 4 people who were using program 1, 2, and 3. And people are basically using these different mixtures of either using program 3, maybe not program 2, or whatever the case may be. And so we want to draw these sets. But here the way that the sets will end up working out, we don't want kind of male, female, all of that kind of stuff. Here we're distinguishing based on program 1, program 2, and program 3. And so the people in the middle over here, for example, in this region, are using program 1, 2, and 3. So maybe we could call these sets, each calling them by a number would not be a very convenient naming sort of a strategy. Would it make sense to call them A, B, and C still? A can be program 1, B can be program 2, and C can be program 3. At least then we don't need to mix things up. And so give it your best shot, this problem. I'm not going to describe it here. I hope that it will be a fun little exercise for you guys. But hopefully the previous problems have given you enough clues about how to approach this one that it should be very doable. So anyways, thank you guys for watching this video. I hope that it was a help to you. And if you have any questions, I would love to expound more on any of these problems or on other problems that you would like to see as well. So anyways, have a great day.